Vector proofs. Let's go. Rhombus. We're wanting the diagonals to be perpendicular. If these are vectors, then the dot product of those two vectors would be 0 if they're perpendicular. So there's our challenge, is to do the dot product and get 0. So, what do we know about a rhombus? So let's go, the distance between O and A is the same as the distance between A and B, because all the sides are equal. So AB, BC and CO are all equal. We can also say that the vector OA is the same as vector OACB, and the vector OC is the same as AB because it's a rhombus. So let's get those green vectors. OB is easy, so let's do it first. OB is going to be OA plus AB. I guess we could have called them letters as well, it doesn't really matter. AC is going to be the negative of OA plus OC. Okay, let's dot product them together. So OA plus AB is a vector, and the dot product of that with OC okay, at some point, so this is the dot product, at some point you will have done a distributive law. So the dot product is distributive. So OA dot OC is the first term minus plus minus, it's an arrow, there's our dot product. Okay, what can we see? Let's go with, can you see this OA and OE? And we've got OC and AB are the same from up there. So if I write it, because OC is also AB, minus AB dot OA, they cancel. Clearly we're fighting time here, so I don't want a big long video. I'm going to do this twice anyway. AB. AB is OC. So AB is OC. Now, looking at that dot product, if I've got a vector and I dot product it with itself, then the dot product is AB cos theta. If theta is 0, cos is 1, so it's just the magnitude of one times the magnitude of the other. So it's really just OC. OA, and we actually see up the top here that OC and OA have the same magnitude. So that distance and that distance are the same. So when I subtract them, I get 0. And that's it, QED. You've proved that the dot product of those two green vectors is 0, hence they're perpendicular. It might take you a little bit to actually get the connection between those two. Just draw a vector somewhere and dot product it with itself, and you'll see that it just comes out. Anyway, let's do that again because that was so much fun. This way's, I don't know whether it's easier or not. So let's go this time. This is I'm going to set that as the origin and go, this is vector A, and I'm going to set A as, well, A0 because it's on the x-axis. Let's go red. There's vector B. So B is, I don't know. Oh, that's dodge, isn't it? I should have gone the other way. So X, Y. Importantly, the magnitude of A equals the magnitude of B. The magnitude of B, B is the square root of, so we can say that the square root of x squared plus y squared is actually A, or, now I don't know whether you can see that, but that's Pythagoras because that length is A, so that's just Pythagoras. Anyway, that's going to come in handy later on. We do need to go back and go, well, we're back to these two green vectors and we're wanting to dot product them. So we're wanting to dot product the green one. The first green one, the first diagonal, the first green one is going to be A plus B. The other diagonal, I haven't labelled them this time, is going to be minus A plus B, because we're going minus A plus B. Okay. This time we actually have what A and B is. So A plus B is actually A0 plus xy, and B minus A is going to be xy minus A0. And they are two vectors, and we're going to dot product them. Right. Okay. A plus x, y. That is one vector. The other vector is x minus A, y, and we're going to dot product them. I guess I can x plus, put it the right way. So when I multiply those two things together, that's the difference of two squares, which is x squared minus A squared, and plus y squared, which is x squared plus y squared minus A squared. Oh my gosh, look up here. What's x squared plus y squared? A squared. What's A squared minus A squared? 0. Two ways of doing proofs. Awesome. If it's an external exam, I don't know that they can force you to pick a way. You've just got to find a way to do the proof. Hope you enjoyed.